Hi there, this is Heath. We're on the day 9 notes. We're just going to look at a couple of examples of mistakes that beginning proofwriters sometimes make. None of you will be making these mistakes, but I'd like to go over them anyway, and talk about ways that we can avoid them. So that's all we're going to look at today, is just a list of common mistakes. One is arguing from an example. When you don't really have a good, strong understanding of how to prove something, but you can demonstrate it with an example, sometimes people substitute that example for the proof. Typically, this doesn't happen for very simple proofs, like proving that the sum of two even integers is even. But as they get more and more, as the proofs become more difficult, people tend to want to just sort of fall back on, I don't know how to say this in general, but here's an example. So let m equals 14 and n equals 6, and n plus n is 20, and that's even, and that's what I meant. It's an example, but it's not a proof. It's not a good way of proving something. If we want to prove something in general, we have to prove it in general. And so don't do this. It's an easy fallback method, but it's not a good proof. Another common one, and it's one that I do once in a while, not often, but it's one that I still sometimes fall into the trap of doing, is not keeping track of which letters I've already used and repeating a letter that I've already used to represent something new. So if you know the definition of what it means to be even, and you say let m and n be even, so m is equal to 2k and n is equal to 2k, that's saying that this k and this k, if they're the same, then you're only proving this for cases where the two even integers are the same. And if you meant these to be two different values, you should have used two letters for them. That is, either way, this proof is incorrect, because one is proving that the sum of two of the same integer is even. The other one is making use of k to represent two different things, and that's not allowed. So keep track of which letters you've used. Don't repeat a letter if you want to use it to represent something different here. So you can't let n be 2k and n be 2k unless you really mean that m and n are the same number. And most of the time, that's not what you want. Skipping over a step. People do this sometimes when they're in a hurry or when they're down to the very bottom of the page, and they skip over a step and they think that it's okay to go ahead and do that. Let m and n be even integers, then m is equal to 2j for some integer j, n is equal to 2k for some integer k, then m plus n is equal to 2j plus 2k, and therefore m plus n is even. There's something that's missing here. What goes here? Let me fix my pen here so I'm not erasing with it. Well, you want to first of all write this as 2 times j plus k. And then you want to specify that j plus k is an integer for some reason. Why? If you haven't specified that, you can't conclude that this is an even number yet. And so leaving out the step of saying, by the closure axiom, j plus k is even. J plus k is an integer. So something's been left out. It's obvious. I know you know what you're doing at this point. Once you can show this is 2j plus 2k, you can see this has a 2 in it, this has a 2 in it, it's even, but there's a step missing from the proof. It's not a full proof without that step. So don't skip over little details trying to get to the conclusion. Again, this is one that tends to show up more in later proofs as things become more advanced, is to use the theorem that you're proving as a step in the proof. So if we want to prove that the sum of two integers is even, let m and n be even integers. Since the sum of even integers is also an even integer, then n plus n is an even integer. Therefore, n plus n is an even integer. I'm hoping you're laughing a little bit at this, but what happened here? The person writing the proof wanted to show that m plus n is even, and they're using the fact that when you add two even numbers together, you get an even number. And that's a true fact, but it is the thing that we were trying to prove. And so you haven't written a proof that the sum of two integers is even. You've written an argument that goes around in circles. You're using the statement to prove itself, and you can't do that. So don't do that. It happens, but avoid it when you can. Confusing what needs to be shown with what has already been shown. A lot of times when the calculations in a proof get hard, somebody will do some scratch work on the side, working backwards from the conclusion to try to figure out what it is they need to start with. And so then when they start to incorporate that scratch work in the proof, because they're working backwards from the end, they are incorporating something out of step, out of order. So if we want to prove that the product of two odd integers is odd, we might want to start from the product, that the product of these two integers, m times n, is something that we can write in the form 2s plus 1, for example. And then we might work our way back and figure out a way to prove this. And then in the proof we write, suppose m plus n are odd integers. And our goal is to prove that m plus n is odd, which means there is an integer s such that mn is equal to 2s plus 1. Now, we didn't show this. This is a goal for the future. We didn't show this. It's a goal. It was the idea of what the end step in the scratch work was, and then we work backwards from there. And the person writing the proof continues, says, well, by the definition of odd, there's an integer a plus a and b, such that m is 2 times a plus 1 and n is 2 times b plus 1, and therefore 2 times a plus 1 times 2a plus 1 times 2b plus 1 equals 2s plus 1. Well, what's wrong here? What's wrong here is that we have established that m is an odd integer and n is an odd integer. We still have not shown that m plus n is an odd integer. This was just a goal. And so we don't know that these two sides are equal yet. We pulled the 2s plus 1 down from here, but this was a statement of what we were intending to show and not what we've already shown. And so we can't then say, well, since s is an integer, mn is odd. This step is not valid because we're taking something that we have shown and making it equal to something that we were intending to show but never got around to actually showing. And this, like I said, tends to be evidence of somebody who has worked backwards through a proof and then tried to incorporate their scratch work into the proof. This step hasn't happened yet. This is out of time, out of order in the steps. And since it hasn't been shown yet, you can't use it here. Okay? All right, let's keep going. This is an easy one to fix. This is one of the easier ones, using the word if rather than since. We use the word if a lot when we're talking about molecular statements, when we're combining statements together into an if-then form, where P is an unknown and Q is an unknown, and then we say if P then Q. But when we're proving something and we have already made the supposition that P is a prime number, this is no longer unknown. We don't know whether P is a prime number. We know that it is, because that is our first statement to prove. We could have also written the word assume here, but we're making the assumption that P is a prime number. And therefore, since this is not an unknown quantity, this is not something that could be true or could be false, and we have to make a truth table to determine, we know that this is true because we have assumed it. And so we can then say, since P is prime, then P doesn't have any factors other than P is 1. And then we can keep going. But we're no longer representing that this is a statement that could be true or could be false, and its truth value is unknown. It's known, and since it's true, we can say, since this is true, then since follows. So don't use the word if after you have already assumed or established that something is true. Okay? And then the last one. This is a confusion over quantifiers, and this one tends to be more something that people who are English language learners also have more trouble with this than people who use English natively. And so if you're an international student, you're not necessarily at more risk for this, but you are sort of in the category of people who sometimes have trouble with this because in their native language, these quantifiers may be used a little differently. Like a statement that says that there is at least one of something. Proves that there is at least one integer x, such that x plus 2 is equal to 7. And then the student responds, well, 5 is the only integer, such that x plus 2 is equal to 7. And so there's exactly one integer x and not at least one integer x. So the statement is false. This doesn't make the statement false. Exactly 1 is okay. At least 1 means it could be 1 or it could be more than 1, but it's not contradicted if it turns out that there's exactly 1. This leaves open a possibility that there's more than 1. And in fact, that possibility doesn't need to be left open because there is in fact exactly 1 integer. But it's not wrong logically to leave it open. It just doesn't. It could be a stronger statement, but this statement is still correct. And so this is not a proof. Okay? So this was a short video today, but this is the last video before the test on Wednesday. There is a practice test on Canvas, and on Monday we will just go over the practice exam. We'll have some face-to-face sessions on Monday. If you want to come by and ask questions, even if you're not in the Monday section, clear it with me first so I can make sure that we're not having too many people show up in the room, but we have been having extra seats left over on Mondays. So have a great weekend. We'll talk later. Bye.